Hey guys, welcome back, and this is lesson 1.8 about polynomials and inverse functions. So let's get cooking talking about these topics. So first thing we're going to talk about are some properties of polynomial functions. Feel free to pause this and take any notes that you need. So a couple things about polynomial functions that we're going to be using throughout calculus. So polynomials have a domain of all real numbers. You can input anything into a polynomial function and get an output. They are continuous everywhere, which kind of follows from them having a domain of all real numbers. Continuous means that they have an input everywhere. There are no discontinuities. They have end behavior, which means at extreme ends of the graph, they're either going to approach positive or negative infinity. The degree of a polynomial is equal to the largest degree of a term of the polynomial. So basically what that means is if I have something like, let's say 6x squared plus 8x minus 9x to the fourth. This would be the term that determines the degree because it has the largest power. So the degree of this polynomial would be 4. And this -9 here would be called the leading coefficient because that's the coefficient of the term with the highest degree. Polynomials can have relative minimums and maximums. What that means is graphs can do something like this. Each of these points would be a relative minimum or maximum. These are also referred to as turning points. So any of those are relative minimums and maximums. Then for any polynomial of degree n, the polynomial can have at most n-1 relative extrema. So these relative minimums and maximums are the relative extrema or turning points, and the polynomial can have at most n-1 of them. So this one has 1, 2, 3, 4, 5. So this graph could show a 6th or higher degree polynomial. Actually, technically, we talk about end behavior because one side is going down and one is going up. This has to have an odd power, so this is actually a 7th degree polynomial or higher. And then all polynomials must have a y-intercept. This also follows from the fact that polynomials have a domain of all real numbers. There has to be a y-intercept because when you input 0, there must be some kind of output value, which would be the y-intercept. So we're going to talk a little bit about end behavior. So we mentioned end behavior here. They either approach positive, negative, infinity, extreme ends. So we can use this table to determine the end behavior of a function. Basically what this is saying is if I have an even degree and a positive leading coefficient, my end behavior will be up. So to the left side, so as x approaches negative infinity, I'll approach infinity. And to the right side, as x approaches infinity, my function will approach infinity. So an example of this is x squared, which is a parabola. It goes up on both ends of the graph. If I had a negative leading coefficient, so like negative x squared, it would do the opposite. On both the positive and negative infinities, as x approaches both positive and negative infinity, the function would approach negative infinity. With odd degrees, one side goes up, one side goes down. So for example, x cubed looks something like this. And if I have a positive leading coefficient in odd degree, as x approaches infinity, f of x will approach positive infinity. As x approaches negative infinity, f of x will approach negative infinity. And then negative x cubed, so negative leading coefficient, would do the opposite. Left side up, right side down. Feel free to pause this and take some notes on this table. We're going to keep moving. So we're going to talk about one-to-one functions. So one-to-one functions are functions where over an interval, each input has exactly one unique output value. What that means is none of the output values repeat either. So if a function is one-to-one over an interval, it's said to be monotonic, which means over that interval, the function is strictly increasing or strictly decreasing. So one way that we're going to check one-to-one functions is graphically, we can use something called the horizontal line test. So you've learned about the vertical line test, which was something to check whether or not a function was a function. Because if a vertical line test touched the function more than one time, then it couldn't be a function because there were two outputs for one input. So we can also use the horizontal line test to make sure that every output has exactly one unique input that maps to it. So we think about one-to-one functions because if a function is one-to-one over an interval, so let's say we have a function f of x is one-to-one over an interval, then that function has an inverse, which the notation here is that f -1, f to the negative first. This is not the reciprocal of f, it's f inverse. So this is read as f inverse of x. And if the function is 1-to-1 over an interval, then f has an inverse over that interval. So we're going to talk about how to find an inverse algebraically first. So to find an inverse algebraically, we're going to let the input be x and the output be y. We're going to swap the input and output variables, then we're going to solve for y. Once we've solved for y, we'll get the inverse function. So we're going to take a look at what that looks like. So here's an example. We're going to find the inverse of f of x equals 3x minus 7. So first, we're going to let the input be x and the output be y. The input is already x, so we're going to change the output, which is f of x to y, equals 3x minus 7. We're going to swap x and y. X equals 3y minus 7. Now we're going to solve for y. We're going to add 7, divide by 3. So y is equal to x plus 7 over 3, which now if we want to use the inverse notation, which we do, f inverse of x is equal to x plus 7 over 3. So that's just a quick example of how to find an inverse function. We're going to use these definitions of inverse functions when we're finding derivatives, and there are going to be specific derivative rules that go along with inverse functions. So let's talk about some properties of inverse functions that we need to make sure we know. So if we have two functions, so we're going to say that we have f of x whose inverse is g of x, then we know the following things. So the domain of g of x is the range of f of x. The range of g of x is the domain of f of x. Basically, for the inverse functions, the domain and range swap. And we also know, this is a fact, that the graph of g of x can be obtained by reflecting the graph of f of x over the line y equals x. And that transformation, if you remember from geometry, if we look at points on the graph, what that transformation does is if we have the point AB on one graph, then the point BA must be on the other graph. And it kind of makes sense when we think about how we solve these algebraically. We swapped the input and output, so the graphs will swap the x and y coordinates of the graphs. So last one, number 4, this is going to be an important way to verify inverses. So when we verify inverses, last time we talked about composite functions. If we make a composition of functions, g of f of x or f of g of x, in this case, you're going to get the same thing if they're inverses, and it'll be x. So basically, what we can think about happening here is g of x and f of x are inverses of each other. So they undo the operations the other function does and leaves us with solely the input value, which is x. So we're going to do one of those. We're going to verify that g of x and f of x, these two functions right here, are inverses. And we're going to do this both ways. First, we're going to find g of f of x. So if we have g of f of x, this is x plus 7 over 3. So I'm going to input f of x. So that is 3x minus 7 plus 7 over 3, which this is pretty easy to simplify. Is simplify. Negative 7 plus 7 is 0. So I'm left with 3x over 3. 3 divided by 3 is 1. So this is just x. So g of f of x is equal to x. Therefore, these two must be inverse functions. Which means I actually don't need to verify this algebraically because I know that g of f of x is x. Because they're inverse functions, the properties of inverses must apply, which means that f of g of x must also be x. But we're just going to show it algebraically to show that we will also get x out of this. We're going to do f of g of x. So f of g of x would be 3 times x plus 7 over 3 minus 7. If I distribute the 3 in here, 3 divided by 3 is 1, so I'm left with x plus 7 minus 7, which is equal to x. So both ways, f of g of x and g of f of x, we get just x as the composition. So thank you for sticking with me. I know that was a lot of information all at one time. I hope that you took some notes, and I hope that you are ready to ask questions in class. The two major things we talked about today were the properties of polynomials and then inverse functions. Within the properties of polynomials, we also talked about one-to-one functions, mostly for the purpose of making sure that we understand when inverse functions exist. And they exist when a function is one-to-one over an interval. So thank you for taking your time to listen. If you have any questions, you can let me know, and I hope you have a fantastic day.